So with the photoelectric effect, brief summary here, you have got all of this information on a couple of additional handouts that I gave you. During the photoelectric effect, which is essentially that electrons are kicked out of a metal because the metal absorbs photons. During that process, every single photon that strikes the metal is absorbed by one and only one electron. I mentioned yesterday that an individual electron cannot absorb multiple photons, which is kind of weird. Even if the two photons happen to hit the electron kind of at the same time, the electron will absorb one of them, but not both. I'll mention now kind of the opposite thing, or a similar idea, that a photon cannot be absorbed by multiple electrons. A photon can't hit two electrons and be kind of split. Forgetting about the photon that is absorbed by an individual electron for a second, an electron is held to an atom on the surface of the metal by some force. It's an electric force. And in order for you to remove that electron from the atom, you have to do work. It's no different than if I decided to be silly and take a toonie and glue it to the floor and watch people walk by and try to pick it up. Sooner or later, somebody will get it. They just have to apply enough work to that situation. They have to add enough energy to be able to remove it. That energy required to remove the electron is called the work function of the metal. Every different metal has its own work function. We'll actually learn in Unit 4 what the work function really is, and it's sometimes called the binding energy of the electron. If the photon does not have enough energy to overcome the work function, which means the photon energy is smaller than the work function, then the electron doesn't get to leave the atom, which means it's still part of the metal. If the photon's energy is more than the work function, and what that means is the photon has more than enough energy to remove the electron, then the electron will leave. And the key idea here is the electron's kinetic energy, once it's out of the metal, is found by taking the energy that the photon gave to the electron. Because when the photon hits the photon disappears. It's no longer there. The energy is absorbed entirely by the electron. The electron's kinetic energy outside of the atom, which means when it leaves the metal, will be the photon energy minus the cost of freedom, which is the work function. In terms of formulas, you've got all these formulas swimming around in solving these problems. You have energy equals hc over lambda, and energy equals hf. These two formulas very specifically designed for photons. You also have Ek equals a half mv squared, and Ek equals qv stop. And I think it's probably the case that it might say Ek max on this formula, but it's not really that important. Don't let it confuse you. These two formulas are designed, well, the bottom formula is designed specifically for electrons during the photoelectric effect. The top formula is designed for any particle with mass, which an electron is included in. So we would say that these are formulas you can use for electrons. On the other hand, you also have this formula, work equals hf0, and that's not really for a particle or a photon. What it's for is the metal. It's for the work function. You should also understand why increasing the brightness of the light will produce more electrons, which means a greater photoelectric current. You should also understand why increasing the frequency of the light will produce electrons with a greater kinetic energy. You get more electrons if you use brighter light because brighter light is more light, and more light is more photons. So each photon kicks out an electron. If you have more photons, you're going to get more electrons kicked out. Increasing the frequency of the light produces electrons with greater energy because when you increase the frequency of the light, you increase the amount of energy that each photon carries. And each photon gives all of its energy to the electron, so if you increase the frequency, the photon energy goes up, the energy transferred to the electron goes up, and the electron will have more energy left over when it uses up some of that as the work function. Does anybody have any questions you'd like me to go over from this entire section? Go ahead, Farhan. 18, certainly. What is the wavelength of a 5.7 million electron volt photon? So there are a couple of questions. I think number 1 is kind of like this, and number 18 is kind of like this, which really don't have anything directly to do with the photoelectric effect, but they have something to do with photons, which we learned about to understand the photoelectric effect. What this question is about, I wonder if I have it here. Yes, it's about this. It's about the fact that I can call that photon a 5.6 million electron volt photon, or I can call it a 2 times 10 to the negative 13 meter photon, or I could call it by whatever its frequency is. And I don't know that that wavelength I just said is the right wavelength. That's what the question is. And the bottom line is, if you know the energy, you can find the wavelength through the formula E equals hc over lambda. So if we use this formula, energy of the photon equals hc over lambda, we can go ahead and put that energy in, and we have an option here that we could convert it to joules. I'm not going to. There's something that's not optional, and that's that you need to address that mega. Capital M in the metric prefix system is mega, and if you look on your formula sheet, because maybe you've forgotten some of these, it's there. It says mega equals 10 to the 6. I believe it's on the side of the formula sheet that has constants on the left, math, trigonometry, that kind of stuff on the right, and then down the middle of the road on that side of the formula sheet are all of your metric prefixes. So I'm going to put in here, Farhan, 5.7 multiplied by 10 to the 6 EV equals, now we might be tempted to use the 1242 thing, right? That will work. It's just that when you do it with visible light or ultraviolet or infrared, your electron volts are like half, 1, 2, 3, 5, 6, 7 electron volts, and your nanometers are like 5 to 1,000 or 2,000. If we do this and take 1242 EV nanometers over lambda and cross multiply, we're going to get a very, very tiny number of nanometers, which I hope kind of makes sense, because look at the size of that energy. It's 5.7 million electron volts. Visible light, I'm going to go back to the diagrams, some of them that I've shown you before. Here are some typical run-of-the-mill electron volt energies of visible light photons. So clearly 5.7 million electron volts is not visible light. It's probably gamma. In fact, I'm pretty sure it is gamma. So if you cross multiply here, you're going to end up with 1242 divided by that number. And you get this number of nanometers using the 1242 shortcut. Now, I'll just make sure I wrote that down correctly. We won't worry about the rounding because I'm going to carry the decimals on my calculator if I needed to. This is lambda equals 2.18 times 10 to the negative 4 nanometers, but a nano is 10 to the negative 9. So if you multiply that together, you're going to get 2.19 or 2.1 whatever multiplied by 10 to the negative 13 meters, which is the answer to the question. You certainly didn't have to do the 1242 thing. You could have put up here 4.14 times 10 to the negative 15 times the speed of light over lambda, and that would have taken you to this number already in meters. Is that okay? All right. Any other questions? Go ahead, Willis. Okay. I don't know if what I'm about to tell you really rings true or makes sense. But before the photoelectric effect, you have a piece of metal, and you have an electron in here, and you have a photon. Now, I don't know how I should draw a photon. Usually what we do, even though it's not a wave that we're talking about, is we do this. There's our photon coming in. And that's the before. And really, the only thing with energy before is the photon. Okay, the electron, I mean, the atom might be in motion, but it doesn't play a part in the electron being removed from the atom. The electron essentially has no energy. It hasn't interacted with the photon yet. And then afterwards, you have that piece of metal and you have the electron. For whatever reason, we don't need to get into it. The electron turns out to be ejected basically perpendicular to the surface. And the photon is nowhere to be found, right? And we have this energy. And this is the part in my mind that's confusing about the photoelectric effect, is if I want to talk about conservation of energy, the energy before is hc over lambda. The energy after is not 1/2 mv squared, because some of this was used up by the electron to get out of the metal. And the difficult thing is we can easily say part of that energy went into the work function, but it's very difficult for me to explain to you where that energy is. Where is that energy now? Like, where is the energy when I peel that coin off of the floor? That's a difficult, conceptually difficult thing to understand. I will tell you right now, this is not a perfect explanation or analogy, but it does the job. If I were to remove my phone from this table, it requires energy, doesn't it? Like, if I just pull a little bit, it doesn't move. But if I do this, I've removed it. Well, what has happened is the energy that I use to remove it is now potential energy. It's gravitational potential energy. And since this electron was attached to a positive nucleus with an electric force, when you remove the electron, you're actually adding electrical potential energy to the electron. And I'm telling you that the energy of the photon has to be the sum of these two. Now, we'll get to the question in a second. You could have instead just said, and I like this much better, that the kinetic energy that the electron gets to keep is always going to be equal to the energy of the photon minus the work function. To me, I don't know. Don't be honest here when I ask you this. I want you to be honest. Does that make more sense than talking about the photon's energy going into the work function and kinetic energy? It does to me, and I think I see a lot of nods here. It does make more sense intuitively to look at it this way. Either way, Willis, we have enough information to calculate the energy of the electron. In fact, we're told the energy that the electron has. And we have enough information that we can calculate the energy of the photon using hc over lambda. So whether we say that hc over lambda equals this plus this, or we say ek equals hc over lambda minus w, we're off and running. This is 1.2 eV. Is my memory right? Did I see 1.20? And it was 400 nanometers? 410. So this we can calculate as 1242 over 410. minus W. So what we're going to have here, I might as well use numbers. I was just going to say we're going to have a number, but let's find out what they are. 1.20 equals, I'm going to divide the 1242 by the 410, and I hope everybody recognizes that I'm almost forcing everybody to get used to the 1242. I don't really give you too many options here. This is 3.03. So minus W. As much as this top relationship, which I'm going to highlight to you, as difficult as this top relationship is, it makes more sense in this context than where we are here. 1.2 equals 3.03 minus W. At this point, you're just solving a math equation. You're not even really thinking about what's going on. But if you do solve this, you're going to get the work function equals 3.03 minus 1.2. And let me explain to you why this makes sense. The photon had 3 electron volts of energy. The electron took all of that photon's energy, but it was only allowed to keep 1.2. So the question becomes, well, where's the other 1.8? It was spent getting out of the metal, which is the work function. And if you decide to rewrite that instead of 1.8 or whatever, it's going to be 1.9, 1.77 or whatever, you can multiply it by the conversion factor of 1.6 times 10 to the negative 19 joules per electron volt. Go ahead, Ben.
Would you be able to subtract that work function, or like put over the HE over lambda on the other side, and then since you get a negative number from that, you multiply the negative symbol in front of the W to get a positive answer?
Sure. If I understand you right, from here, I just want to make sure. Is this what we're talking about? Definitely. I just prefer, and I'm in a math mode right now, not to have negatives in front of an unknown. I like to move it to the other side of the equation to make it positive. Absolutely. Here you would get negative 1.8, or whatever the exact number is. Negative 1.8 equals negative W, so then you would say that must mean W equals positive 1.8. Any other questions? Farhan?
So if the energy of the photon is less than the work function, the electrons will absorb the energy of the photon, but they won't be removed from the other.
Correct.
But it'll be like the energy will be absorbed and it'll be converted to heat and whatnot. And if an electron absorbs the energy of the photon, is that like permanent? Could it not absorb any more like ever?
No, it can absorb another one later. But so let's just imagine that you could fire individual photons at a very specific electron, which is a technological feat. I mean, that's amazing. But each of those photons has less energy than the work function. The first photon would hit, it would heat up the atom. And by the way, it would be equivalent to, this is just an analogy, so I guess it's not equivalent. It would be equivalent to me trying to remove this 3-hole punch from the table by hitting it. And I didn't hit it hard enough. I didn't add enough energy to the system to remove it. But if this were an electron and the table were the nucleus of the atom or the rest of the atom, what would happen is the whole atom would move. And it would move faster than it was already moving because atoms have atomic motion. So the next photon comes along, it would heat it up, it would heat it up, it would heat it up. In other words, if you shine, say, red light on a metal, and that red light is, the photons in it are less energetic than the work function, which means the frequency of the red light is less than the threshold frequency. Electrons will not be ejected, but if you touch that piece of metal after a while, it's going to be warm. Have I answered your question?
Yeah, and also like if the, let's say the photon is half of the work function, it's never going to be possible that you just come up at 2 of the photons, one electron.
Apparently not. Correct. You know, it's been a very long time since I've taken university physics, but even in fourth year quantum physics, when we apply the photoelectric effect, I seem to remember that it was always, no, it's a one-to-one relationship. Nature is funny that way. The two photons can't team up or gang up on an electron and get it to pop out.
And visible light is the only type of EMR that has photons?
No. Oh, no. Definitely not. Every EMR consists of photons. This is good we're having this conversation. Every EMR form can behave like a wave when it interferes and diffracts, and every form of EMR can behave like a particle. In other words, every form of EMR consists of photons. And we're back to that, well, which is it? Are you telling me light is photons or light is a wave? I'm telling you it's kind of both. It's one at times and another at times. But going to your original question, X-ray photons, gamma ray photons, ultraviolet photons, radio wave photons, these can all be photons.
So, like, let's say you have an X-ray photon.
Yep.
Instead of increasing the brightness, you increase like, the intensity of the source.
Okay, just a second though. Did you just say instead of increasing the brightness, you increase the intensity? But intensity is brightness.
So that would be like in a different form for it. No, okay.
These things are produced, X-rays are produced in a different manner than visible light.
No, I see what I just said because like they're the same thing, but with visible light you can actually see it.
Yes. You know what you can think of it as being like, and I think this is an interesting conversation. We're getting a little away from the photoelectric effect, but I think it's interesting. You can think of it like sound, and this is really stretching it because sound is not electromagnetic. Sound is a mechanical wave. Can you hear every sound frequency? No. There's a range of frequencies of sound waves that if the air is vibrating too fast, you don't sense that as a sound, and if it's vibrating too slow, you don't sense it. I'm sure many of you are aware there are these certain pitches that younger people hear that older people don't. I have one on my phone. I'll start it up one time. That they broadcast this in areas where they don't want teenagers loitering. And it's really annoying. But I can't hear it because my ears have aged. So, your eardrum, which is the antenna for a sound wave, which is a mechanical wave, can oscillate in a lot of different frequencies. If your eardrum is capable of oscillating with a frequency of 500 hertz, 500 times per second, and it is if your hearing is good, then when I strike a 500 hertz tuning fork, those bars, or they're called tines on the tuning fork, vibrate back and forth 500 times per second, knocking the air molecules next to it back and forth 5 times per second, and it's like this accordion effect moving from the source to your ear, and eventually those air molecules, water molecules, nitrogen molecules, oxygen, all those molecules are tapping on your eardrum 500 times per second. Since your eardrum is capable of vibrating 500 times per second, it triggers a sensation in your brain which you call sound. Well, there are receptors on the back of your eyeball. There's something called the retinal sheath, and these retinal cells have electrons on the atoms. I shouldn't say electrons. These retinal cells have charged particles. I don't know if it's electrons or ions or what, but they are only capable of vibrating with a certain frequency. So when it vibrates with a frequency of, I have to do a calculation here because I'm ashamed to admit I don't know the range of frequencies for visible light. I only know the wavelengths. Let's say we had a wavelength of 500 nanometers. If I take the speed of light divided by 5 times 10 to the negative 7, 500 nanometers corresponds to a frequency of 6 times 10 to the 14 hertz. The little pieces of that retinal sheath are able to oscillate back and forth that many times per second, which is amazing. Something in the back of your eyeball is going back and forth that many times per second. And because it's able to physically do that, your brain creates a sensation, which we call color. But just like your eardrum is not capable of oscillating at any frequency, neither are the parts of the retina, neither are the parts of the retina able to oscillate at any vibration. So really we're back to bring this thing to a closure, we're back to the idea that all of those forms of EMR are really the same stuff, whether they are electromagnetic waves where you have the electric wave moving up and down and the magnetic moving in and out, or whether they are photons. What distinguishes visible from the other ones is we can just see the visible. We can't see the other ones. I hope I've answered your question. I hope other people got something out of that little lecture. Any questions before we move on today? Any other questions? All right then. So we're going to do a quick investigation today of the photoelectric effect in terms of a graphical analysis. And this is a kind of a special graphical analysis, one that you don't have to set up each time. When we've done graphical analyses before, we kind of compare the slope to something and the y-intercept to something, but there's like a dozen different graphical analyses. This is one that you need to remember, I think. So we have already said that Millikan, when he measured the kinetic energy of the electrons in his experiment, and by the way, he didn't measure the kinetic energy directly. What Millikan did was he measured the stopping voltage and multiplied it by the charge. This is how Millikan was able to determine the kinetic energy of individual electrons. When he plotted that kinetic energy as a function of the frequency, he got this line. Now, we've seen this graph before in our notes, but I didn't put this part in here, right? I just said to you, well, that makes sense. That has to make sense because very low frequencies of light hitting a photocell or a metal do not immediately cause electrons to be ejected until you reach a certain frequency. And by the way, this frequency right here is in fact the threshold frequency of the particular metal. And that feature of the graph has nothing whatsoever to do with a graphical analysis of y equals mx plus b. It's simply a fact of the matter that that's the threshold frequency. I shouldn't have said that. We could explain it in terms of y equals mx plus b, but I'd rather not just yet. So what we are asked to do is compare this physics equation to the equation of that line, because it says just relate the equation to the graph. There's lots of information on the graph that connect to the photoelectric effect. Well, this is a straight line, which means it must obey y equals mx plus b. And there is not, let me restart that sentence. And the graph doesn't go through the origin. And it shouldn't go through the origin, right? Think about that. If it went through the origin, that would mean that a radio wave photon would always cause electrons to be ejected from any metal. Because as soon as you get any frequency, you get an energy coming out. So this is a direct comparison. When we take a look at this, it's pretty simple, I think, to understand that the maximum kinetic energy, let me get a better color here, that the maximum kinetic energy is what's plotted on the y-axis. The frequency is what we plot on the x-axis. So by comparison, what that means is that Planck's constant is the slope. And in fact, I don't know if you remember that, but when we learned about this is what the graph looked like the other day, we said, well, Millikan is a curious fellow. He found the slope, and guess what? The slope is equal to Planck's constant. Well, that's why the slope is equal to Planck's constant. Now, we want to be careful here. This is not the work function. And I haven't lost my mind, but I'm being technically very careful in what I label that as. It's not the work function. Anybody know what it is? Farhad? It's the negative of the work function. It's not the work function. The y-intercept of this graph is not the work function. It's the negative of the work function. Because I can very easily up here where I have minus w put plus negative w. And then my comparison becomes complete. I have plus b plus negative w. So we need to know on this graph that the y-intercept is the negative of the work function. A work function is a positive number. When you look at the y-intercept, it's a negative number. So you have to take the negative of that work function. Sorry. You have to take the negative of the work function to get the y-intercept, or the negative of the y-intercept to get the work function. Okay? I'm not going to bother handing out rules for this first example because I'm going to draw the line up here. And if you want to draw a line with some kind of straight edge, you can. But we're just going to be working off what you see here. A group of physics 30 students perform a photoelectric effect experiment, and they plot their data as shown. So this is the data that we get. And the top point is labeled as point A. So I have mentioned this before, very rarely, but it sometimes happens. On a diploma exam, they give you a graph where they have not drawn the line in. So if we want to know the features of this graph, I guess we could do a linear regression. That would work. So what I'm going to do, let's test my ability here against a linear regression. I'm going to draw what I believe to be the line of best fit, and that's not it. I'm going to adjust that. That's a tough one. Boy, that's a tough one. I would say that's the line of best fit. I want to just move it a little bit. Okay, I'm going to go with that as being the line of best fit. Okay. So what's this first question? I hate this question, but I see it on diploma exams quite frequently. This is not a physics question. This is a math question. What's the slope and what's the y-intercept? So to find the slope, if you went with this, and you can follow along and write stuff down or not. We're just in a very kind of a learning mode right now. You would need to take 2 points on this line, which I'm going to make thinner. You would need to take 2 points on this line, and I'm going to go with this one here, and I'll go with that one. Neither of those points is precisely on the crosshairs of the grid, but it's close enough for what I'm interested in. If I wanted the slope, I would take the rise, which is from 0.6 to 1.7. That rise is 1.1 times 10, not even times 10, 1.1 electron volts. And my run is from 6 to 9.5. Correct me if I'm wrong, that's 3.5. So my run would be 3.5 times 10 to the 14 hertz. So I need to take for my slope 1.1 EV over 3.5 times 10 to the 14 hertz. Since a hertz is a per second, that's going to turn into electron volts times seconds. So I get 3.14. Do you get the same number? Okay. So according to my graph, the slope is 3.14 times 10 to the negative 15 eV seconds. Now, what is the y-intercept? So in order for you to, this is why I really don't like this problem on a physics exam. This is now really a math problem because I can't even extend this line to see the y-intercept. I can't. Because I don't have a grid. And by the way, extending this line and trying to estimate the y-intercept is a really bad idea. So what I need to do is say y equals mx plus b, and I have y equals 3.14 times 10 to the negative 15 x plus b. So if I want to find b, I need to put in an ordered pair. That's really, there are other ways that you could do it. I'm going to put in this point, I'll put in this point down here, which was 7 multiplied by 10 to the 14, comma, 0.6. So I'm going to put 0.6 here. I'm going to take the slope that I got and multiply by the 7 times 10 to the 14, and then I have plus b. So I need to take 0.6 minus that product. Incidentally, as I've told you before, it's been a couple of years since I've really looked at a diploma exam. I think they've really gone away from giving you just the data points. They normally give you a line. But let's see what we get here. The answer times 7 multiplied by 10 to the 14 gives me a y-intercept of negative 1.6 eV. Scary that it worked out to like exactly negative 1.6. But so the y-intercept is negative 1.6 eV. So our answer here would be, the slope is a point B, that would be 3.4. No, it would be 3.1. And the y-intercept is negative c point D, c is 1, D is 6. That's what we would get if you did it with my line. Let's do a linear regression. This is going to require a little bit of work, but one of the expectations in this course is you can read data from a graph. I'm going to erase all this. I don't think we need it here. So I am going to go Stat, Edit. I have all kinds of stuff in my list, so I'm going to go to my Memory menu and clear all my lists. So back to Stat Edit. I'm looking at these points, everybody, left to right. So I am looking at the first point. I'm going to number these 1, 2, 3, 4. Which, to be honest, whoever designed this experiment didn't do a very good job because 4 data points is not good enough. You should have at least 6, I would say. So that first data point is at, I'm going to say it's at 5.2. Times 10 to the 14. The tick in between the 5 and the 6 is 5.5, so I think that's 5.2. The next one I would say is at 6.4. Remember, your X goes in list 1. The third one I would say is at 6.6. And I would say the fourth one is at 8.5. I'll double check that. 5.26. Yeah, that looks good. So what are my y coordinates? Starting at point 1, it's 0.2 eV. Then it's, okay, I got to think about this. This is 0.5. This is 0.4. I would say that that data point is 2/5 of the way there. So 0.42. Could you live with that? If you said 0.41, I wouldn't argue. It's kind of a toss-up. I think many of you would want to say 0.41. So I'm going to say 0.42. The next one is, I would say it's almost exactly halfway between 0.6 and 0.7, which would be 0.65. And the last one, we get a break here, is 1.4. So now I'm going to do the linear regression to determine the equation of the line of best fit. I like to do this from the home screen. I don't know that you have to go in here, but if I then go Stat, Calc, LinReg, my line was not drawn very well, was it? Well, I think with 4 points, it's pretty difficult to see exactly where the best fit is. I would still say that my answers are good answers. And I think this is precisely why the diploma exam has gone away from having no line drawn. Because you could draw the line and you could draw the line and they get totally different answers. So anyway, if you went with the linear regression, it would be 3818 instead of 3116. Okay. But let's go with, for this, let's go with the calculator for the rest of the questions. What's the threshold frequency of the metal? Well, I do believe the best thing for you to do here is to use the formula work function equals Planck's constant times the threshold frequency, except, so we're going to go with the numbers from the calculator. The work function was 1.84 eV. And Planck's constant is not the number on your formula sheet. Planck's constant is the number that we get for the slope of the line. In fact, I believe the next question will be asking you about the Planck's constant somewhere. There it is. But we need to know from the very top of this lesson that Planck's constant is the slope. So I can put in here 3.75 times 10 to the negative 15 times the threshold frequency. So you get about 4.9 times 10 to the 14 hertz. So our answer to number 2 would be 4914. Let's go back to my line, because I don't think there would be anything wrong if you were given the line. There would be nothing wrong with you extending the line. That's as close as I can get, I think. And reading the x-intercept, because the x-intercept is the threshold frequency. And I would say that's pretty close to 4.9. Times 10 to the 14. If you take a look at the data point for point A, how much kinetic energy are the electrons ejected with for data point A? Now, the thing I want to draw your attention to is these two numbers are out of this world. They're crazy. You're not going to have an electron with 1 joule of energy. Electrons have electron volt energies, which is 10 to the negative 19 joules, 10 to the negative 18 joules. And all we have to do for this question, everybody, is look at the fact that it's 1.4 eV. You're told the kinetic energy of that data point. The electron for that data point has a kinetic energy of 1.4 eV. So for question 3, all we have to do is take 1.4 electron volts and convert it to joules by multiplying by 1.6 times 10 to the negative 19 joules per eV. And getting, I'm guessing 2.2 times 10 to the negative 19. Number 4, what's the experimental value of Planck's constant? Well, we already determined the slope. And again, I'm going to choose to go with the slope from my linear regression. The slope was 3.8 times 10 to the negative 15. So why is the answer not 3815? I'm telling you that if you put 3815, it's wrong, even though I've told you the slope is Planck's constant. Evan? Right. Our graph had units for kinetic energy of electron volts, so this was electron volts times seconds. We want joules times seconds. So we're going to take this number, we're going to multiply it by 1.6 times 10 to the negative 19 joules per electron volt. That will cancel the electron volts in that Planck's constant and introduce joules. So I would say 6.1 times 10 to the negative 34. That would be in joule seconds, which means the answer would be 6134. We have one more thing we want to talk about, and this is not the photoelectric effect. Sometimes as the diploma exam evolves, we see as teachers questions that all of a sudden come out of nowhere and seem to be a standard question they ask, even though it's not really directly in the curriculum. And this is one of them. It turns out that X-ray production, I'm going to pause there, X-ray production. If you were to go back to the very first day of this unit, page 1 of your notes, and look at how X-rays are produced, they're produced by accelerating electrons to a very, very high speed, and then they stop by hitting a metal target, and you produce X-rays. Well, I'm going to be very specific here and tell you what's happening is each electron that stops loses all of its kinetic energy, and you produce a photon. It's the opposite of the photoelectric effect. In the photoelectric effect, you have photons being absorbed by electrons, and the electrons move afterwards. They get kinetic energy. In X-ray production, you use a voltage to accelerate electrons, and then when the electrons stop, all of that kinetic energy is suddenly turned into a photon. So the question here says, if we had an accelerating voltage of 4,000 volts, I don't really care what the anode is made of. If the accelerating voltage of the electrons is 4,000 volts, what's the wavelength of the X-rays produced? Okay, and then we'll explain about the work function. So I want you to calculate using potential difference equals change in energy over charge. I want you to produce or calculate the kinetic energy of one electron, but I want an answer in electron volts. So you know the charge of an electron, and you know the voltage is 4,000 volts. But this formula only works with joules. There is no exception to that. So if I want you to calculate the kinetic energy of each electron because of that accelerated voltage, you have to calculate it in joules and then convert it to electron volts. I'll give you a minute to do that. Did any of you know what the kinetic energy is in electron volts before you started this little calculation? A couple. It's 4,000, isn't it? Because it's an electron and those are volts. If you do take the charge times 4,000, I believe you're going to get, and you will have to just confirm this for me, I believe you get 6.4 times 10 to the negative 16 joules. So that's taking 4,000 volts times 1.6 times 10 to the negative 19 coulombs. But then in order for you to determine the kinetic energy of the electron in eV, you have to divide that number of joules by however many joules there are in 1 electron volt. And that's 1.6 times 10 to the negative 19 joules per electron volt, which takes you back to the 4,000 eV. You with me? Okay, so I want you to answer this question then. What is the energy of 1 photon that's produced when this electron stops? How many of you have the answer to that? Nobody, eh? It's that number, yeah. In fact, we can say it's 4,000 eV. What this is telling you in this question is that X-rays are produced by accelerating electrons to a high speed. The kinetic energy that each electron had is converted to a single photon. So if each electron gets 4,000 eV of kinetic energy, that means each photon has 4,000 eV of energy. And we are asked for the wavelength of that photon. So really what we are doing now is the calculation of question 18 that Farhan had asked about earlier on in the class. You know the energy and you want to find the wavelength. Well, the wavelength will be hc over E. And I think it's legitimate to use nanometers for X-rays. I think 1242 over 4,000 is a good thing to do here. 1242 eV nanometers over 4,000 electron volts of energy per photon gives me 0.3, very close to 0.3. 0.3 what? 0.3105? So I'm going to say 0.31 nanometers, which is 0.31 times 10 to the negative 9 meters, which is 3.1 times 10 to the negative 10 meters. Oh, 10 to the negative 10, X-ray. That was a set of numbers I wanted you to try to remember. We're kind of done. I want to make a point here before we answer the last part of this question. That although I have seen this question on diploma exams where they basically tell you everything that's in the box, I've also seen questions where they just say, in an X-ray tube, if the accelerating voltage is 4,000 volts, what's the wavelength of the photons? So you're kind of expected to know that this is the process. I want to tie this back, before we finish this, to what Farhan and I were talking about, intensity and numbers of photons. If you were trying to take an X-ray of something, but the material was very, very dense, then what you would want to do is get photons with more energy, which would mean you'd have to increase the voltage. However, if you were taking an X-ray of something, they took an X-ray of a bone, and they could see the bone and the fracture, but it wasn't enough detail, then you would want to have more photons hitting the X-ray film, so you would increase the current. You would somehow get more electrons to be accelerated. But the intensity and the number of photons are the same thing. I I'm only asking this second question. Why don't we worry about the work function? Because I have had students say, if it's the exact opposite of the photoelectric effect, why are you not worrying about the work function of the metal? Does anybody know? Ben? Oh, that's true, yes, but that means that when the electron embeds itself in the metal, we should get that work function energy back instead of losing it to removing it. And I will tell you right now, the work function, it does play a role here. We do get that energy back, but why don't we care about it? Naya?
Because it has nothing to do with the amount of energy that the photon receives?
Actually, and I am going to say, the photon does get all of the electron's energy plus the work function. It does get it. But there's a reason why we don't have to concern ourselves with it. It's there. I'm not saying why isn't it there. I'm saying why don't we care? That's right. Look at the energy of this photon. It was 4,000 electron volts. What's a typical work function energy? Well, in the problem we just did, it was 1.8 eV. And I don't know, we could look up the work function of tungsten, which is a typical metal for an X-ray tube, but it's nowhere it's a drop in the ocean. Maybe that's an exaggeration, but it's not significant because the work function is very tiny compared to the energy of the photon. With the photoelectric effect, with visible light anyway, the work function is a significant chunk. Basically, X-rays have so much more energy than the work function. When X-rays hit any metal, electrons come flying off. Anyway, you have some questions here. I'm not sure why I put 1 to 5, 7, 9, and 10 as opposed to 1 to 10. I don't know if that's what's on your handout or not. Is it page 51, first of all? That area. So work on those problems. I need to just do a couple of quick things at my computer. I'm going to turn the speakers back on. Please let me know if they start hissing again so I could hopefully fix it.